Recording is rolling. It is Thursday, August 29th. So here's agenda for today. Do you guys see those folders hanging from the lab tables back there? Right, so I have returned all your guys' graded assignments. They're by class. You guys in front of me have the yellow tags, and then your names are alphabetical order. So if you want to go back and collect any papers that you turned in, graded and turn them all there. Okay, so we are going to go over some more of these puzzles. Yesterday, I went over two of these scenarios with you guys. You guys remember these are linear motion questions. So every single scenario involves some kind of linear motion. Might be constant velocity, might be you throw a ball in the air, throw a ball down from a cliff. It might be a car brakes to a stop. Actually, we're going to look at a couple of car brakes to a stop today. What we're going to do. Okay, so that's and mostly we're going to use these formulas to solve these. So I'll help you guys out with the notice set there. That's what we do. Then later on in class, we're going to do a reaction time lab. So this one I've been promising you guys recently. You guys remember this here? So you guys know if you drop a ball off a cliff, if you know how much time it's been falling for, you can calculate how far it fell. Isn't that this right here? Height is 1/2 gt squared, which is just a version of this right here. X is 1/2 at squared. Okay? But can you calculate the other way? Like if you pair with a partner, so you got two different people, right? One person drops the roller, the other catches as fast as can. You can know how far the roller fell. Can you back calculate how much time it's been falling for? So we'll do that later today. Hope you guys. So I just want to plant that idea now. Hope you guys thinking about that, but hope you guys out a little bit later. All right, then we should have some time in class. So you guys can, of course, finish the lab and turn that into the grade tray. I'll show you guys the setup for that later. And then whatever time you have left, go ahead and work independently on these puzzles, or you can help each other out or ask me any questions. I can help you out too if you get stuck on something. Let's have this page due on Tuesday. Also, there's some graphs on the back. I'll also get you guys started on these, what we're going to do. Okay, so let's have this due Tuesday. So you'll have today to work on it. You have some time tomorrow. We got a 3-day weekend coming up for Labor Day. Right, and then I'll pick this up on Tuesday. I think that'll be a good amount of time. All right. I think I'll use this video for all my classes. My AP students have an additional assignment. My AP students are doing some college physics puzzles. I'm just assigning ones that are circled. Again, that's only for my AP students. But I want to throw that in the video. All right, so you guys good with agenda, what we're doing? All right, so back to the top here, puzzle scenario. Solve a puzzle scenario with you guys. All right, so yesterday we did these scenarios. Let's go over to this one, number 11 and 12. Remember, each scenario has two corresponding questions. Right? So zoom in here. This one said, car brakes to a stop at some given acceleration. Okay? Now pause right there, because one thing I want you guys to notice in this class is all numbers have attached units, and these numbers mean things. So it's a good idea to kind of keep track of like what are like reasonable values for these numbers. Okay? So but you guys know Earth free fall is how many meters per second squared? About 10 meters per second squared. Okay. So what did I put on this car? So I gave you guys a negative value. Oh, because it's braking to a stop. That's why acceleration would be negative. It's braking to stop. Now, my paper, everybody's numbers are different. Mine says 13 meters per second squared. So negative 13 meters per second squared, which is actually a pretty big number. But to put that in context, you would be slowing down a little bit faster than the rate of free fall gravity. But of course, it would be horizontal, right? Now, how reasonable is that? That's like a really good rodent set of tires. So this is related to a physics principle called coefficient of friction between the tires and the road that we'll talk about a few weeks from now. But I just want to plant this idea so that you weeks from now, oh yeah, I remember talking about the car braking to stop. So what if you're driving and the car is wet? Do you think there's like it takes a lot of road to come to a stop if the road is wet? But what if you have a dry road, you have new tires on the car, and you can zip to a stop pretty fast? But that would correspond to a larger magnitude of acceleration, wouldn't it? Okay. I can tell you this is actually a pretty large like deceleration rate. But anyway, just to put that a little bit in context, it takes the car given time to come to a stop. Okay, so somebody's watching this car brake. Maybe got a video recording, and they're saying like how much time did it come to a stop? Okay, so we got that number. I gave that to you right there. Okay. Oh, guys, and the fact that the car came to a stop, that right there is also a kinematic variable. What does that mean? Car comes to a stop tells you what in terms of physics? Final velocity is 0. Okay, so I did explicitly type that number too. Final velocity is 0 meters per second. Again, just to This idea. Right? You open up a physics textbook or go to college and get the same question. You guys know that they're not going to explicitly type that number. Right? You have to, that would be implied. You have to think, oh, I know, final velocity must be 0. Okay, so with all of that, the two questions are, how much road does it take to come to a stop? And look, all the answers are in meters. And furthermore, how fast was the car going before you started braking in the first place? Oh, look, and these are all in meters per second. Right. And there's an exact answer to each one of those. Right. The car had to have been going at some speed and had to have covered so much road for these exact given values to play out the way they do. All right. So most of the puzzles on this page, including this one, a good thing to do is to go back to these kinematic formulas that we've been applying over the last week or so, and go equation chopping. You pick an equation. If you plug in numbers and it doesn't really work out, then a good thing to do is just to go back and pick a different equation and try it out. So here's what you guys know. You guys know final velocity is 0. Okay, you guys know that. You guys know the rate the car was slowing down, that's acceleration. Okay, that shows up in all 3 of these. Okay? And you guys know the amount of time that it took to come to a stop. Okay? So with that starting information, which of those formulas, first, second, or third, do you think is a good candidate to start with? The second one. I like that one too, right? Because that's the only one that would have, at this point, one unknown. Like if you pick one of the other ones at this point, okay, well, I don't know this distance, and I also don't know the initial velocity. So that's 2 unknowns. That's too many unknowns. This last one, I don't know the initial velocity, and I don't know the braking distance again. That's too many unknowns. This middle one, that's a good choice. If you write that one down. So let's do that. So this is number 11 and 12. It's gone. I'll give you guys a little picture too. So road, car, initial velocity that we don't know yet, some braking distance that we don't know yet, and then final velocity, of course, is 0 meters per second. Okay. Yeah, let's do what you guys said. Final velocity equals initial velocity plus acceleration times time. Okay. Now I'm going to do something a little fancy. I'm going to split my paper. I'm going to solve this 2 different ways. I'll solve in terms of variables over here, right? Which I really try to get my AP students more to do. We're solving for and then I'll plug in the numbers first, right? Because maybe that's more intuitive, possibly. So I could plug in 0 meters per second for final velocity. Okay. See, I don't know the initial velocity of the car yet, right? So that's unknown. Okay. I do know the rate the car was slowing down. Now my paper says -13 meters per second squared, right? Which is crazy good, but we'll go with that. And the time was 3.5 seconds. Right? Remember, all these numbers have units attached. Right? You guys got that? Okay. So this feeds in there, this there, this one there, this one. See, all these numbers are feeding in. Right? Guys, right? And I'm solving for how fast was the car initially going for all this to play out. Right? And we can solve that right here. Right? Guys, good? So in terms of variables, actually, there's only one algebra step. All I have to do is very simply subtract over the AT. So final velocity minus acceleration times time. That's how fast the car was going. And that could be the answer there. Okay. Isolate the V0. Okay. On the right side, I've got the same setup, just the numbers plugged in. I can subtract this over. Ooh, guys, if you subtract a negative, that gives you a what kind of number? A positive. So I'll go ahead and write it that way. We'll say 13. That's meters per second squared times 3.5 seconds. Right. It represent, the initial velocity of the car. All right, guys, right? Calculator time. It's that times that. Okay. So the initial velocity of the car was, okay. Whoops. The number on my screen says this. But because that number has units attached to it, what are the units on that number? Meters per second. Bam, meters per second. Okay. And from 2 perspectives. Look at the calculation. Meters per second squared times seconds. One of the seconds goes away. That leaves you with meters per second, which, here's the other perspective, describes the speed. Hey, so that's got to be it. And then, of course, I check my multiple choice, make sure that's an answer choice, and that would be. Guys, so double check, make sure I got, yeah, oh, that was the answer, number 12. That was number 12. But we still got to figure out the other question is, well, how much braking distance was that? Right? How much road? Something in meters. So we got to go back to these kinematic formulas. Oh, all right. So the braking distance, which one do you guys want to use now? First, second, or third? First, yeah. All right, good call. I like that one too. Right. So you actually kind of have an option. Right? We've exhausted the second one already, so we're done with that one. Right. Actually, we know all the variables except for x. Do you guys think you could really use either the first or the third? Right, you could do either one. Now the third, you have to do some algebra shuffle, but I like that you picked the first one because that one you don't actually need any algebra anymore. You just do arithmetic. You just plug everything in because we got all this stuff. So let's do it. Let's go. Distance the car goes is initial speed times time plus 1/2 AT squared. Just like that. All right, all we gotta do is plug in. This is already set up to solve what we're looking for. So how far the car goes is, okay, so I just found this was 45.5 meters per second. The braking time, that was a given value. So that was 3.5 seconds on my paper. Something probably different on yours. Plus 1/2. Oh, don't forget that acceleration was negative. So that's important too, that you have that negative sign. Of course, that's meters per second squared. And then the braking time again, 3.5 seconds. And don't forget 2 squared. Right, just like that. Oh, speaking of that square, let me just double check and make sure everybody's on board here. Guys, what exactly is being squared? Is only that time being squared, that time t? Or is the entire 1/2 AT being squared? What's being squared? Just the t? Guys, show of hands. How many guys think it's just the t? Just the t being squared? Yeah, just the t. Okay, just want to make sure that everybody thought that. Right, so let's do a calculator time. So the distance the car brakes is got 45.5 times 3.5. So many meters. And then I'll go ahead and pull this negative out here. So I'll say minus 1/2 13 3.5 being squared. That's so I'm getting on my calculator screen 79.6 and then a bunch of digits. And the unit is what, guys? What's the unit? Meters, because that would describe a braking distance. Aha. All right, just like that. Just like that. All right, that worked out. Like I said. And like I said a minute ago, had you applied this third kinematic formula and solved for x that way, there'd be some more algebra steps, but you would get the same answer. You can try it if you like. All right, guys, good? Okay. All right, so next thing, I do want to show you guys a graph of that same story we just did. Guys, could this be a car braking to a stop? Actually, it's one of your posters. I think it's a poster hanging in front of me somewhere up here that we went over also yesterday. Okay. Right. So here's velocity versus time. The car had some initial velocity. We had to solve for that, but we got that. It was braking at some rate. So some slope of this curve, that's the acceleration. Right? It took some time to come to a stop. There was some amount of road that took, right? And all those properties are embedded in that graph right here. So, right? And I definitely want to show you this graph because that's gonna help for this next puzzle. Are you guys ready for the next puzzle? All right, here we go. Let's skip on down to the very last scenario. You guys see number 19 and 20. It's another, a car brakes to a stop again. We got another car braking to stop. Only this time I'm giving you a different mix of information. Right? So I told you the braking time. Look, I gave you the braking distance. Ooh. And the fact that it brakes to a stop. What could you say about final velocity again? Yeah, it's going to be 0 meters per second. Okay, so that's 3 kinematic values. So this is solvable. Okay. Now, I'm not going to solve this while I'm out in class, but what I do want to do is help you guys out a little bit. Guys, this is the only scenario on this entire page that if you apply the equations at face value, you're going to run into trouble a little bit. Right? Here's why. Because look at what you don't know right away. You don't know the rate the car was slowing down, acceleration. And you also don't know the initial velocity of the car. Right? But look at the equations. There's A and there's V naught. Bam, bam. Next equation. There's A and there's V naught. Bam, bam. Next equation. There's A and there's V naught. Bam, bam. You guys see if you have this particular scenario that you can't start by any one equation, is that? So there's 2 ways you can solve it. You can either do a system of equations, do some algebra, do some substitution, right? That's a little complex, but you could do that, right? Or I can tell you a faster way to solve it. the faster way to solve it is actually with a graph. Doesn't this graph also explain that story, right? And you can just use geometry properties of a triangle, because that looks like a triangle, doesn't it? So what do you know? You don't know this V naught, and you don't know this A. Okay. But guys, could you say the area of this triangle is 1/2 base height? Oh, I was going to ask you guys, but you guys would have said that, right? 1/2 base height per triangle, area of a triangle. And the base represents the stopping time, and the height represents the initial velocity of the car, right? And the area of the triangle represents how far it went. Right? Okay, and then the slope represents the acceleration, right? So if you play off geometry, you can actually solve it faster that way. I just want to throw that idea out there. If you want to use the equations and do system of equations, you can do that too. Right, guys, right? Okay. The other thing I want to do with you guys on this page is get you guys started on the graphs on the back. There are 3 scenarios on the back, and they're mostly graph questions. And then there's a few little calculations at the end here, right? Now, all these scenarios you guys have seen in little bits so far in this class. Actually, some of these are like straight up posters that I made for you guys that we've already gone over. Okay, so let's read them. Scenario 1. A car starts at some origin point, travels in a positive direction at constant speed all the way to its destination. Oh, look at the questions. What's x versus t? So this is x in meters versus time in seconds. What's v versus t? Velocity in meters per second versus time in seconds. What's acceleration? Meters per second squared versus time in second. Yeah, it's the same set of axes you guys have seen over and over in this class, isn't it? Right? I don't want to do the whole thing with you guys, but maybe I'll set up just one of these. How about velocity versus time? So, guys, you guys know constant velocity all the way to its destination. What does this v versus t graph look like? What is constant velocity? Is that velocity that's constant? There's a velocity that's constant. Constant velocity. That would have to be that. Right? I bet there's a poster floating around that we've gone over the last few days, maybe in your thumbnails possibly, that that finishes the story. You guys think? Right? Right. Okay, next scenario. A car starts from rest at some origin point. So maybe it's sort of hinting you're allowed to put that point on that. Speeds up in a positive direction at constant acceleration, and then slows down at constant acceleration until it reaches its destination. Right. This one's a little trickier because it's like a 2-parter. There's 2 parts to the story. All right, so you're in a car, you speed up, hit the gas pedal, and then you hit the brake, slam to stop. Okay. Can you guys put it all together? So again, I'll give you guys a little hint here. Let's look at velocity versus time. Okay. Right. So, maybe you start at rest. Start from rest. That's that point right there. Starting from rest. Right. Guys, speeding up uniformly. What does that look like on a v versus t set of axes? Yeah, direct relationship. Okay, so that could be the first half of that story. That's hitting the gas pedal. Speeding up. The slope represents the acceleration. Do that too. Slope is acceleration. Okay. But then you slam the brake. What does the rest of this graph look like? Goes back down to 0. Exactly, because doesn't your final velocity have to be 0 meters per second right there? Makes sense, right? Right. Now, if you look back at the posters from last few days or in your thumbnails, I bet you have this as one of your posters. I bet you have this as one of your posters. And of course, it tells all 3 graphs for that. I wonder if you can put those 2 ideas together. That was a little tricky, but I'm curious to see how many students are going to figure that one out. Okay. Next scenario. Balls dropped from the edge of a cliff on Earth. Define the top of the cliff as the origin point. So I'm giving you guys this point here. Down is positive, just like we've been doing all along. Ignore air drag, just like we've been doing all along. Okay. Again, velocity versus time. What does that look like? Drop a ball off a cliff. Is that a zip? Is that direct relationship? Okay. And does the slope of this represents the what? Yeah, the gravity field, which is the type of acceleration. Exactly. Right. Now this one, I asked you guys some numerical questions. So let's take a look at this. Suppose the ball falls for so many seconds. Oh, here I gave you guys a gravity field here. The ball falls for so many seconds. How far did it fall? Do you guys remember Paul Hewitt? Drop a rock. It fell for so many seconds. How deep is the rock? It's about 125 meters deep. How'd you know that? College? Isn't that this right here? X is 1/2 AT squared, right? Or here's a little bit different version of the same thing. That's this right here, isn't it? Isn't this the college equation? Well, for 5 seconds and 10 meters per second squared, 125 meters deep. College. That's this right here. This is the college equation. That'll answer that. Next question. How fast was it traveling when it was about to hit the ground? Ooh, how fast? That sounds like a velocity question. You guys think you could pop in the time and get how fast? Okay. Oh, third question. On a velocity versus time graph, what is the area between the curve and the time axis, for the entire story? Okay, so the area under the curve. Ooh, guys, on velocity versus time, what is the area under the curve? I just hashed it in. What does that area represent? Here, let me ask the same question in a different way. What is speed times time? Distance, distance. You can call this distance in general, or maybe h for height change, right? Hey, how many of you guys think that maybe these two boxes are kind of the same thing, right? How far did the ball fall? What's the area under V versus T? Think that you should get the same number, I hope. Get a little check right there. And last question, on a velocity versus time graph, what is the slope of the curve? Oh, which I guess I just talked about. You guys just told me. So, I bet you guys get that. Okay. All right. So you guys got a good start on that? Good start? All right. All right, so next activity. If you guys have a blank piece of paper, and if you guys see one of these half pages, go ahead and pull up one of these half pages. Everybody's got a half page. Right. Write your name at the top. Name. Everybody wrote their name. You guys got your name? Right. And let's do a title, Reaction Time Lab. Reaction time lab. All right. You guys are about to figure out what is your reaction time. Now, so there's reality playing out in the world, and then there's your brain processing that. Right? Your brain is receiving sensory information through your senses, right? It makes sense of that. Okay? And it feels like all real time. Guess what? It's not. Not exactly. There's a little bit of a time delay. You're driving in a car. Deer runs out in front of the road. You think there's a little time delay before you can process that and slam the brake? Right. How much time is that? You're going to know before you walk out of class today if you do this right. Okay? Now, to calculate your reaction time, how many guys think you need a stopwatch? No, nobody says that. Nobody says that. No stopwatch. We're not going to use that. How many guys think we're going to use a ruler? This is your measuring tool. This is your only measuring tool. Well, this plus the calculator. Let's do it. Ruler plus calculator. That's what we're going to do. Okay. Now, we've been solving this puzzle like forward in time for last few days. What we've been doing is saying, if you drop a ball off a cliff and it's fallen for 5 seconds, how far did it fall? Oh, about 125 meters. How'd you know that? College. That's this equation. This is the college equation, right? What we're going to do today, what you guys are about to do, is turn that all around backwards. So what if you do this? What if you pair it with a partner? What if your partner's holding the ruler up here, and you got your fingers down here at the 0 centimeter mark? So I got it 0 centimeters. I'm not grabbing it, but I'm ready to grab it like this, right? Then your partner lets go of the ruler, and you catch it as fast as you can, except the ruler will have fallen some distance. Is that true? Suppose you catch it at 17 centimeters. It will have taken some time to fall at 17 centimeters. How much time? Oh, and would that be different on the moon or different on Mars? Because wouldn't this be falling maybe more slowly on the moon or on Mars? So the fact that it fell maybe 17 centimeters, that's going to correspond exactly to some fall time, and that would represent your reaction time. Can you guys algebraically rearrange this and solve for reaction time? Can you guys do that? I think you can. So here's what we do. Right, so you guys got your name, you guys got reaction time lab, you guys got that written, right? Okay. So here's how I'm going to score this. Or here's the whole setup right here. So reaction time lab. One student drops a ruler, a different student catches it as soon as possible. Right? So record your data. I'll give you guys 12 points for that. You guys have seen a few lab tables over the last couple weeks. See if you guys can record some data, maybe numbers, units. Okay? Can you calculate your reaction time? There's 4 points. And once you get an answer, step back and look at it and see that it's reasonably correct. Right? Because there's right and wrong ways to do this lab. I've seen it over the years. So, for example, suppose you do the whole calculation and you get, my reaction time was 3.5 seconds. 3.5 seconds. Does that sound about right? No, that's way too yeah, that's way too long. That's way too slow, right? I mean, your reaction time has to be faster than that, right? What if you get it like 0.002 seconds, 2 milliseconds? Does that sound too fast or too slow? Yeah, that's too fast. That's like probably faster than a fly, right? So, okay, so it's gotta be slower. So it's probably something between those two numbers. See that it looks reasonable, right? And you know, I'll even give you guys another hint. A really common mess up with this lab is matching units, right? Guys, the numbers on the ruler, well, first of all, are you using inches or centimeters? Let's go with centimeters. We're looking at metric, right? But these are centimeters. But this gravity field, guys, what's one value you could use for gravity field? 10 what? Meters per second squared. Meters per second squared. Guys, if you use meters per second squared here, but you have centimeters here, is that kind of a mismatch in units? It got something to do with meters, something to do with centimeters. Do you think you have to reconcile those units first? Right. So if you catch it at 17 centimeters, how many meters is that? How many centimeters in a meter? 100? 100? Ooh, is that 2 decimal places? Right. Right? You guys got that? You guys see that? All right, with that, I'm gonna wrap up this recording and yeah, you guys go ahead and do the lab. I will walk around and help you guys out.